Thank you, Babette, and I really would like to thank all the organizers for this invitation. So good afternoon, everybody. I'm going to show you a compilation of three studies on flow of immersed granular media. So I'm going to show you experiment, really model experiment, and two-phase continuum modeling that we use to model this experiment. So this work was done by several former PhD students, Malika Oriemi, Loïc Rondon, and Clément Nobili. Three former postdocs, Michael Paya, Julien Chauchard, and Franco Tapia. And all this work was done in really strong collaboration with Elisabeth Guazelli and with Olivier Pouliken. So our main motivation comes from what we observe in nature, and we are interested in a configuration where there is a really strong coupling between the liquid and a granular media. So, for example, a really first example is a sediment transport in a river. In this case, it is the action of the fluid which erode, transport, and deposit the particle. And I would like to show you a really interesting application of a dramatic effect of this transportation of particle in Taiwan on the Laonang River. After a typhoon, they have to build a new bridge, not because of the bridge was completely destroyed by the flood, but because of the bridge was completely buried in the bed river. So here you see the new bridge, the top of the new bridge, and here you see the top of the old bridge. That means that the bed level of the river grow by something like tenths of a meter, really tenths of a meter. So another example, which can be really catastrophic, it's the case of landslide. So in landslide, we know that this event occurs when the soil are completely full of water, full of liquid inside. In this case, also in Taiwan, I love Taiwan. So in this case, you can see that there is water in the highway. So the soil is completely full of water. So our approach is to do really model experiment, really simplify experiment, when we want to understand the physical mechanism at place, and then to develop a continuum description to predict, to model this flow. So the first experiment we developed was to study bed load transport by a laminar shearing flow. So in this case, we use a rectangular tube, which is 1 meter long, 6.5 centimeter height, and 3 centimeter width. And in this tube, we put an index match combination of fluid and particle. So the fluid and the particle have the same refractive index. That means that we can see what's happened inside the layer. So we use a spherical bed of borosilicate or PMMA, which are 2 or 1 millimeter in size. And we use a fluid which is really viscous, 300 times the viscosity of water. So we are in a viscous regime. So we impose a flow rate using a flow loop and a pump. And we're looking what's happening inside this test section using a laser. So here you can see a sketch of the experiments. So the fluid is made fluorescent using rhodamine. That means that we use a filter, and then the particles appear black, and the fluid light gray. And we seed the fluid with some small particle. So that means that we can do a PIV, particle image velocimetry, to get the velocity profile both for the fluid and the particle. So Bernard spoiled my movie, but I'm going to show it again. So you can see that the particles are transported by the fluid till a given position. And then we do PIV. So in red, you will see the velocity profile of the particle, and in blue, the velocity profile of the fluid. So that's a time evolution, because what's happening is that the tube is not fed in with particle. So with time, there is erosion, and the level of the particle decrease. And that's why the transport of particle decrease also. So what is really interesting to note on this video is that the fluid and the particle have the same velocity inside the moving layer. So from the gray level intensity, we can also get some information about the fluid thickness here, and about the volume fraction. So I have to say it is an estimation of the volume fraction, because it's really difficult to measure really the true volume fraction. So what we see is that at the beginning there is a dilation, and then we see that the fluid thickness increases with time, but this increase is quite slow. this 4 millimeter in about 200 seconds. So we can think that we are in a quasi-steady uniform regime. And then in this movie, you are going to see in red the particle velocity, and in green the volume fraction. So what I want you to note is that the volume fraction is nearly constant all over the bed, except at the interface, where it goes to 0. So all the change in volume fraction is located at the interface. So we want to model this experiment. And then we decided to use a two-phase model, two-phase continuum model. So I'm not going to go inside the detail of this two-phase model. So you can find everything in the paper from Jackson or in the paper from Babette and Olivier, more recent paper. So the idea is that we consider that the granular phase and the fluid phase are two interconnected continuum phase. And then the continuity equation and the momentum equation, they are obtained using averaging process. So during this averaging process, so here you can see this equation in the case where we are in a low Reynolds number, so we don't have any inertia. And in this process of averaging, in fact, you have three new quantities which come from the averaging. So you have the interface hydrodynamic force, which are negative and positive in both equations. You have the stress of the particle phase and the stress of the fluid phase. And all the difficulty lies in giving a constitutive law for these terms. So that's really the key question. So for the interface hydrodynamic force, we choose to use a buoyancy force and a viscous Darcy drag because we have a really viscous fluid. So now what's about the stress of the particle phase and the stress of the fluid phase? For the particle phase, you are already seen a lot about this mu-phi rheology. So we decide to use a granular rheology because if we are looking to the particulate phase, all the grain interact only through contact. It's only contact interaction. So if you take two grain and you move them together, you will have friction force between the two grain. So now if you consider an assembly of grain, we are expecting that when we use, for example, the simplified geometry of a plane shear under a controlled normal stress, that means that you impose the pressure, you impose the shear weight, and you wonder what is the shear stress. And in this case, we expect that the shear stress will be proportional to the confining pressure with a coefficient, which is a friction coefficient. But what we have seen from granular, dry granular media experiment and for immersed granular media experiment is that, in fact, this friction coefficient is not constant, but it depends on the shear weight. So it depends, in fact, of a single dimensionless number, which can be interpreted differently between like two stress or two time. So here I show you an explanation with two different time. We have, if we look to this little sketch, you can see that considering this particle, there is two typical time. The first time, which is a macroscopic time, which comes from the shear weight. And the second time, we correspond to each time where the particle falls in between other particles due to the confining pressure. Can show it again. So this time depends of if there is a viscous fluid in between or not. So in the case of a viscous fluid, we found that the microscopic time depends on the viscosity and on the pressure. So then you build this J number, which is a comparison of these two typical time, and in fact, which is a dimensionless shear stress. So we can find in the literature, so that's the data by Franco that you've just seen before. So you can see that in the literature, then the coefficient, the friction coefficient depends indeed on the G number, and we can use correlation fitting law that are used in the case of dry granular media. They are nearly the same. They are fitting law. And there is something also very, very important is that the volume fraction also depends on this J number. So for a given J number, you have a given volume fraction. And then we have the rheology for the granular phase. So what about the fluid phase? So if we consider the fluid phase, we can simply follow the work of Jackson and of Kavli also. And the shear stress, the effective stress of the fluid phase come from two contributions. The first one, which is the mean field stress transfer, and the second one, which comes from the particle, from the interaction with the particle. And then if we follow Jackson, we can think that this, the shear stress is simply follow a Newtonian rheology with an effective viscosity which depends on the volume fraction. And it's also built on the volume average velocity. So what do we have to take for this effective viscosity? We know that we should recover Einstein viscosity at low phi. But the question is, we ask, does it depend on the flow configuration? For example, if you take experiments for neutrally buoyant suspension, there are a lot of experiments in this case, so I pick 3 examples. So if you take experiment or numerical simulation, for example, for the numerical simulation of Kavli, they are able to measure the contribution from the fluid and the contribution from the contact. And you have also the experiment by Boyer et al. And also a really, really interesting experiment on shear reversal. So they reverse the direction of the shear. And in all this paper, they found that the effective viscosity should be diverging at the jamming. But now, if we consider our configuration of immersed granular media, they are not neutrally buoyant. So they are all settled. And then, if you look at the community of flow in porous media, what they usually use is simply an Einstein viscosity. And it works well to describe a flow over a fixed particle bed. And now if you take the work that Bernard showed you this morning, if you, in the same configuration that we use, if we look at the contribution from the hydrodynamic or from the contact, we found that for the hydrodynamic, when we are going to low phi, to high phi, for low phi we have Einstein, we recover the Einstein case, and for high phi, we increase a little bit due to the lubrication, but we don't diverge. So for this work, we choose to use a non-diverging effective viscosity. And we think that it is not diverging because it's not the same than neutrally buoyant. Here, in this case, all the particles are always touching. For all cases, also for low phi, in fact. All the particles are touching, so we can think that the long-range hydrodynamic effect are screened. So now we have a completely closed continuum two-phase modeling for viscous dense suspension with the 3 closures we have chosen. So we are going to apply this model for the case of the bed load transport. So if we choose this model, so to simplify in this slide, I choose to use a constant phi because we know it's just changing on the first layer. So we end up that the pressure, the particle pressure inside the bed is simply hydrostatic. If we look at the momentum equation for the fluid phase horizontally, in fact, if you look at the different terms, we found the Brinkmann equation, which is usually used. And if you look at the different terms, this one is really high because the permeability is really low. That means that, in fact, we have a particle and fluid velocity which are the same. That's what gives us the Brinkmann equation. And if we look at the mixture equation, we can find that the total pressure, the total stress increases in the bed due to the pressure gradient. But then there is a transfer from the fluid to the particle. So if you look at this sketch, inside the pure fluid layer, the fluid shear stress increases, and then inside the bed, it decreases while the particle pressure increases. So there is a transfer of stress. So from this equation, we can have we can have an analytical solution if we consider a Coulomb law. We can just begin with a simple Coulomb law for the granular rheology. So thanks to a Coulomb law, we can make dimensional analysis, Coulomb friction with a constant coefficient of friction. We use Einstein viscosity as a first play, and then we can have an analytical solution. And this analytical solution, it gives us the wavelength scaling. For example, the length scale is the fluid thickness. That's the fluid thickness which controls the flow. And the control parameter is a dimensionless fluid flow rate based on the fluid flow rate and the fluid thickness. And another thing is that we found a parabolic velocity profile inside the mobile layer. So if we look at the scaling, they are really the good ones. It scales the particle flux. But now, if we are looking at the detail of the velocity profile, it is not parabolic. So we cannot have the detail of the profile if we use a Coulomb law. That means we need to use something more complex. We need to use a granular frictional rheology. So with the granular frictional rheology, we solve it numerically in 2D and in 3D, and with parameter. So the parameter we have to find is the parameter of the rheology. And with this parameter, we found a good agreement between the velocity profile and the model. So now we are still working on this experiment, but we want to see what's happened when we go from the viscous regime to the inertial regime. So it's an ongoing project with Bernard, Babette, Eckhart, and with Franco and a PhD student, Shangwei Hong. And so we are going to do numerical simulation, we are going to do two-phase modeling, and for the experimental point of view, if we want to, it's really difficult to find particle and fluid we are the same, who has the same refractive index, but with a really low viscosity. So I think we are going to play with hydrogel. I don't know if you know hydrogel. It's a particle which grow in a fluid. And then we already play a little bit with this particle, and we put it in the pressure impulse rheometer with Franco. And next time I will show you the result. But now, for this talk, I want to show you something. I want to go beyond the steady flow, because what I've shown you now corresponds to steady flow. And I wonder what's happened if you go beyond steady flow. Because if we use the frictional rheology for the particle phase, the mu of I and phi of mu of j and phi of j, it's only valid for steady flow. That means that we have to have reached the good volume fraction. But when we are preparing a granular column, we can choose what we want for the initial packing fraction. So we wonder what's happened, what is the role of the initial packing fraction of the granular bed. So then we develop a new experiment, which is a granular collapse in a fluid. So we have a cube, which is 70 centimeter and 50 centimeter for the size. And what we do is simply a granular collapse. So we use glass beads, which are about 200 micron. We use a viscous fluid because we don't want any inertia. And we can change the initial aspect ratio, and we can change the initial packing fraction. So how do we do to change the initial packing fraction? We put the granular media, and then we mix. And that means that we have a suspension. We let it sediment freely, and that corresponds to the random loose packing. And then we tap. We just tap on the cube to have something more compact. So that means that we can choose the initial packing fraction between the random loose packing, which is about this value, 0.55, and the random close packing, which is about this value, 0.62. So the change is really small. So what's happened when we do the collapse with different initial packing fraction? I'm going to show you two movies. The first one corresponds to the random loose packing. So when we open the door, you can see an immediate collapse with a long run out and something quite fast. Now, with a dense packing, when we open the gate, it's completely different. We have only some avalanche by the top, and it's so slow. Yeah. So it's real-time experiment. And at the end, I'm not going to wait to the end. We found that for the loose case, we have a fast, long run out. For the dense case, it's much slower, and we have a short run out. So, and the difference in packing fraction is not so high, from 0.55 to 0.62. So we see that there is a crucial role of the initial volume fraction. And this effect was already noted by Iverson and collaborator. And they propose a mechanism to explain this effect, a pore pressure feedback mechanism. So what's happening if you begin with a loose case? If you begin with a loose case, it's not an equilibrium packing fraction, so it's going to compact. But to compact, you need to expel the fluid. But when you expel the fluid, that means that the pore pressure inside is going to grow, and then the particle pressure is going to decrease. And then, as it is a frictional phenomenon, the friction will decrease, and that's why we will have this really fast motion. Now, if we begin with a dense case, you cannot move if you don't dilate. But to dilate, you need to suck liquid inside the granular media. That means that the pore pressure decreases and the particle pressure increase. That's why it's so slow and there is a delay. So to use to model this phenomenon, this dilatancy, we need to add dilatancy to the two-phase model. So the dilatancy, for the dilatancy model, we use the work of Payan and Pouliken, which is also based on the critical state theory on Roux and Rajai. So the idea is that if you go back to the plane shear geometry, when you make a motion, when you shear, you will see that you have a vertical motion, which can be positive or negative. And that defines an angle, in fact. That defines the angle that we call the dilatancy angle. So this relation. So this dilatancy angle, the main hypothesis is that it depends on the difference between the local packing fraction and the packing fraction at equilibrium. That's the main ingredient. And then this dilatancy angle, we have to add it in two positions. We have to add it to the rheology, because it's when you go down a hill or up a hill or down a hill, it changes the rheology. It changes the macroscopic coefficient of friction. So we add it to the rheology, and it also governs the evolution of the bed to the mass conservation, in fact. So we use this in the two-phase model. And to solve the two-phase model, we also do a depth average two-phase model. So I show you just some idea of this model. So we neglect inertia. We consider that the velocity, the vertical velocity of particle is small compared to the horizontal velocity, and that the vertical size is small compared to the longitudinal size. And that's not true at the beginning, in fact, but let's continue with that. And the variable in a depth average two-phase model is the thickness of the granular media with time and position. So we use the momentum conservation for the mixture. It just corresponds to the fact that the basal shear stress is equilibrates the gradient of the pressure, which is due to the gradient of the thickness. And then for the total pressure, it corresponds to the weight of the particle. And then for the fluid, the basal pressure corresponds to the Darcy flow, in fact. So we have all the ingredients to solve that together with the mass conservation, written in the Lagrangian form. So we just take the rheology at equilibrium I showed you before, and the dilatancy. So we put all the ingredients together, and we solve this numerically. So the model gives us the characteristics dimension for the pressure, the thickness, the velocity, and the time. And it gives us also the parameter of the avalanche. And we found that the main parameter is the packing fraction, as we expect. And there are two other parameters, which are second-order parameters, which is the aspect ratio of the granular column and the aspect ratio of the column compared to the size of the particle. And we solve numerically using a Lagrangian description. So I'm going to show you the comparison between the experiment and the model in white for the loose case. So the shape is not exactly the good one because we have a problem at the beginning, because the model is not well described in the beginning, but we recover the dynamic and we recover the one-out. Now, if we look to the dense case, so the detailed dynamic is not good because in the experiment, the grains are not moving all the thickness, but we have the good dynamic and we have the good one-out. So we can make a full comparison of the experiment. So the experiment is a triangle, the simulation is the dot, and we look at the total duration of the experiment versus packing fraction, and on the shape, which is in fact the angle of this triangle, versus the packing fraction. So what we found is when we are loose means below 0.59, the dynamic does not depend on phi, it's really fast, but the one-out depends on phi. And if we are looking to dense case, the dynamic depends a lot on phi, but the final shape, in fact, is angle of repose. So I have 5 minutes left. I can show you the last experiment. So the problem, so it's working really well. But the problem is that when you are looking to landslide, you are water saturated soil. It's full of soil, but the avalanche is not in water. The avalanche is on air. And we were wondering what happened. Can we do that on an experimental point of view? So we designed a new experiment using the capillary cohesion to build a column on air. So first we measure the capillary cohesion, just considering a discharge, water discharge, through a granular column. And we measure the pressure at the bottom. What you see is that the pressure decreases slowly when the water level decreases. And when you reach the top of the bed, you see a drop of the pressure. This drop of the pressure corresponds to the buildup of the menisci. So due to the Laplace pressure, the pressure inside the fluid decreases. And then when you reach the maximum here, the maximum curvature you can sustain, the air enters the system. So we measure this drop of pressure, and we change the surface tension, the size of the particle, and we found that, as expected, it is a Laplace pressure. But what is interesting is this coefficient, which shows that the pore size is smaller than the particle size. So that's the maximum drop of pressure that a granular media can sustain. And for a particle we use of about 80 microns, it corresponds to nearly 1 meter of water. So how do we build our experiment? We use a tank, which is a square section, which is about 6 centimeters. We put granular media, which is made of glass bed of 80 microns, and water, and we mix. So we let sediment, and then we choose the packing fraction by applying tap. And then we remove most of the water, and then the tank, the cuve, is linked to a water reservoir that we put below the cuve. And then we open this tap. That means that the liquid drains. But when the liquid reaches the interface with grain, there is the pressure decrease. It's imposed by this value, which is below the maximum value we can sustain. And that means that we create a pressure drop in the liquid, and we have something stable. Doesn't move anymore. There is no motion of water anymore. And the pressure drop in the liquid applies a pressure on the particle. It is equivalent to a membrane. So that means that we have this membrane of the top of the particle, and we can tilt the cube just like that. And we end up with a column which is completely full of water, and which is stabilized by a capillary cohesion. So there is no door to open. It's completely stabilized by the capillary cohesion. And then we close this tap, and the sample is ready. So how do we trigger the avalanche? So we found two ways to trigger an avalanche. The first one is just to apply a kick, like we do an earthquake, for example. So I show you the experiment. Here is a column, which is vertical. We apply a kick, and we see the collapse. And we have a collapse of a water-saturated column on air. So what's happened if we change the packing fraction? So that for the random loose packing, you can see that the collapse is immediate. We have a long run out. Now what's happened if we increase a little bit the packing fraction? So the movie is accelerated 3 times. So we see that we have a collapse, but it's going with the velocity is smaller and the run-out is smaller. And we just change a little bit on the packing fraction, and you can see that the run-out change a lot. So it's really, really sensitive. So here is the position of the front with time. So you can see the difference between the different packing, which is not changing so much. And then we observe that there is no collapse above this value. So why? So we come back to the pore pressure mechanism feedback. So if now we have this column which is stabilized by capillarity. So if we begin with random loose packing, when we apply a kick, the media tend to compact. So to compact, it expels the fluid. So that means that the fluid which is expelled completely kills the menisci, kills the capillary cohesion, and then we have the avalanche. But then if we go to the dense case, when we apply a kick, you want to delay it, but there is no water to go inside. And then there is no motion. So we imagine a second way to destabilize the column. So we begin with the same initial state, and then the tap is closed here. We take the reservoir and we put it above, and we open the tap. So it's more like a pressure imposed collapse. So I show you what happened for different volume fractions. First one is a random loose backing. You can see that the collapse is immediate, and it's really the same than in the previous case. Now we increase a little bit the backing fraction. We have the same kind of motion. And now we are going to dense case where there was no motion before. So the movie is accelerated 11 times and 20 times. So the first down case, you can see that the motion is not at all the same. We have a kind of collapse here and here, and it's not at all the same motion. And for the denser case, you can see the first collapse, the second collapse, and the third collapse. And the dynamic is not at all the same. So qualitatively, we can follow the front with time, and you can see this kind of collapse. So you can see that there is a long delay before any motion, and we can see this circular collapse. And then we can just, to finish, compare what happened for the avalanche on air here and for the avalanche underwater. So we can see that the time is not the same. The total duration of the avalanche is not the same. And in fact, it's faster underwater. And then for the final shape, it's nearly exactly the same. So now what we plan to do is to do the depth average two-phase model, just changing the boundary condition to see if we can understand this avalanche on air. So I'm running a little bit out of time. So to conclude, I have shown you that using a continuum two-phase modeling, using the good closure and the viscous down suspension limit, we can apply this model to several experimental configurations. And now we have perspective in the bedload sediment transport to go from viscous to inertial regime, and we need to perform the depth average two-phase model for the water saturated column on air. I thank you for your attention.
Thank you, Pascale. Thank you. Many questions.
Hi, Pascale. Really nice talk. I had a question about the second to last slide, the one that you had 4 different collapses.
Sorry.
I was very surprised by, yeah, the last 2, when it collapsed, you said it's going in pieces, but it seems to be that the collapsed surface is kind of like inverted this way. I would have expected either straight down or the other way. So for the last 2.
Oh, for this one?
Yeah, so it seems to kind of like carve backwards, have a negative angle, like this orientation. So why is that, and why that angle? And so it feels very counterintuitive.
What we understand is, why is it at the bottom? It's at the bottom because the pressure is a maximum at the bottom. So we understand why it begins at the bottom, but the size of the collapse, and no, we have nothing about it, and it's really compact. So no, we have no explanation for the moment, and I'm sure that the two-phase model won't predict this case.
We have done some simulations, some grain resolving simulations of these kinds of granular collapses, and we've looked at the dependence on the volume fraction, and what we find is that as the volume fraction is increased, you generate these preferred failure surfaces, and so I think that has something to do with the orientation and so on. So something that maybe we can look into.
Yeah, yeah, we can discuss.
The wonderful experiments. Are you suggesting that in a real landslide, capillary phenomena could be in play, even though the particles could be much bigger?
I don't know, because in the real soil you have argile. I don't know the English name of it. So the real soil are much more complicated. But there is a really nice experiment from Iverson. I don't know if you know this experiment. It's a large-scale experiment. I got the movie. They are so wonderful. I can show you the movie. I don't know if you know this movie. So he used on this movie, he used real soil. And so he do a dense preparation and a loose preparation. I can just send the movie. And in the dense preparation, they have sprinklers, they put water on it, and it doesn't work, so they put more water and nothing happens, and it's accelerated 5 times, and then you have this failure. But if you, and nothing happens, nothing interesting. And if you go to the loose preparation, so at the beginning nothing happened because there is not enough water, and then it's wow, it's immediate. So I don't know about capillary on this case.
No, but I agree that if it's clays, it's small enough
Yeah,
that capillary forces could be dominant. At least on the left side, it's quite clear that there's a lot of capillary cohesion going on.
So.
Hello, it was a really nice talk. Thank you. I was wondering, is there any treatment on the walls, or is it just glass in those?
No, on the wall, no, we did nothing special. It's Pertex. So, but I was thinking maybe I can try to use different inclination just to do a corner instead of having this top wall. We can change the geometry. Okay. So I think we can play a lot with the geometry of the initial.
And like surface roughness, particles on the walls, things
like
that. Yeah, that's what I was wondering. Thank you.
Bravo.
Pascal, so very nice work. Now, the difference between the dense and the loose packing is that in the dense case, there's enough of a contact network that sufficient stress is transmitted through the contacts and not necessarily lubricated by the fluid, right? I mean, could that be the difference?
Sorry, I did not hear correctly.
Oh, I'm sorry. So, okay. Sorry, I wasn't close enough to the microphone. So, in the dense case, is it not the case that there are enough particle contacts and that stress is transmitted through the contacts and not necessarily through the fluids? So, it's not as though the pore pressure lifts the particles away from each other. Right? I mean, is that the reason?
When we are looking, I think that there are contacts in every case. From 55 is already, it's
55 is random loose packing.
Yeah, so even in the loose packing we have contact, and when in other experiments where we measure the pressure, the pore pressure, we don't find that the volume fraction, we can completely liquefy a granular column without change in volume. So we can change so I think that when we are in the granular state, there is contact, and but I don't know.
Pascal, on the videos you showed, this is a tilted box, right? On the 4 videos you...
Yeah, tilted box, yeah.
This is a tilted box. Yeah. So the top boundary is a rigid surface.
Yeah, exactly.
So the particles are stuck on the surface. So without this rigid boundary, maybe you would not see any of this strange collapse structure.
At the top, we have also this rigid boundary for this case. And it doesn't... so...
Yeah, but there is more inertia here at the beginning, so maybe it can overcome any resistive forces between the particles and the rigid boundary.
So maybe I can start with something like that. With no top, that I can do it easily, in fact. I just have to tilt the cube at the beginning, and maybe I will show something different.
Okay, thanks.
Yeah.
More question? Oh, one question.
Hello, nice talk. Maybe a quick question. You told us that in order to retrieve the parabolic profile, fluid profile, it was necessary to have the right granular rheology. I'm a bit, how come, how it translates the granular direction in the fact to have or not the parabolic.
You should choose.
It was the first part of the talk.
So this profile is not parabolic. If we try to, if we use a Coulomb profile, it won't be the good one. So we think that we need to put the good rheology. But a lot of experiment on granular media shows that we need to put the good rheology.
It reminds me, because we have the same kind of model but with turbulent flow, it reminds me it is relatively we use a very coarse turbulent Rans model. It is relatively sensitive to the mixing lengths we use, and so maybe it is just to do with the coupling of the, what happens at around between -0.5 and 0 on Z, and but it's kind of a mystery.
Yeah.
Okay.
So we found that the granular friction gives a good profile, so, but we don't have. That's why we do a collaboration with Bernard, because Bernard can do a DNA simulation and can have more information on the stress, on the particle, and things like that. So we can compare what we have and answer this question.
Good idea.
Yeah, but I guess the parabolic profile is given by a Coulomb friction,
Yeah.
but it's actually it doesn't work.
It doesn't
actually.
work. No.
Yeah.
Okay. Thank you.
I'll just use the microphone. So in the theory that you did sort of midway through your talk, I was just curious what you used for your bottom boundary condition. Did you have it sort of slipping, no slip, stick slip?
In which case?
You showed the movies where you had a white line superimposed on the lab experiments. So you developed a theory for that white line.
Yeah, on the collapse.
What did you use for your bottom boundary condition when you were solving the equations?
So I have to go back to my work, but for the velocity, it's I don't remember.
Maybe we'll talk about it after.
We can discuss afterwards about that. But
okay, cheers.
It's a shear. It's yeah.
That's a shallow water equation. That's average formulation.
That's average, yeah. That average equation. So we just solve the total stress at the bottom. We don't put a zero velocity at the bottom.
But you don't impose a front condition either, because that's normally done in a shallow water equation.
No.
Okay.
We just everything is closed on the equation now.
Okay. No more questions. So we thank Pascale again.
Thank you.